Hello guys, myself Natasha Kushwa, and today we are going to solve theory of computation assignment questions. In this PPT, we will solve questions, topics that are to be covered in this PPT: context-free grammar, derivation tree for sentences, production rules in Backus-naur form, BNF for postfix expression. So let's move forward to the next slide. Here we this is our first case. In this question we have give some rules for context free grammars to solve the context free grammar questions. Consider the case of a grammar that generates a subset of English. This subset of English is defined using a list of rules that describe how a valid sentence can be produced. We specified that rules, these are the rules for a grammar for to solve context free grammar questions. So what is grammar? A grammar contains a set of rules that can be applied to generate all strings in a language mathematically system for defining a language. Here are some rules to solve these questions. A sentence is made up of a noun phrase. This is the basics of context free grammars we have to understand before solving to the questions. A sentence is made up of a noun phrase followed by a verb phrase. Now, a noun phrase is made up of an article followed by an adjective followed by a noun, or a noun phrase is made up of an article followed by a noun. A verb phrase is made up of a verb followed by an adverb, or a verb phrase is made up of a verb. An article is a, or an article is the, an adjective is large, or an adjective is hungry. Here are some others rules are also in this slide. A noun is rabbit, or a noun is mathematician. A verb is eat. A verb can be eat. Verb can be home. An adverb is quickly. An adverb is can be wildly also. From these rules, we can form valid sentences using a series of replacement until no more rules can be used for instances. We can follow the sequence of replacement sentence, noun, phrase, verbs, etc. So, in this slide, these are the sentence. This is not a sentence. These are the production rules we have given to solve the CFG questions. Articles, adjective, noun, verb, phrase. Article, adjective, noun, verb, adverb. The adjective, noun, verb, adverb. The large rabbit, verb, adverb. The large rabbit hops, adverb. The large rabbits hop quickly to obtain a valid sentence. It is also easy to see that some other valid sentences are a hungry software engineer eats wildly, a large programmer hopes the rabbit eats quickly, and so on. Also we can see that the quickly eats programmer is not a valid sentence. So here in this slide we have given some grammar rules, or there are two terminals we have given. First is the set of terminals and second is the set of non-terminals. In the terminals we have given the sleepy, happy tortoise, hare passes, run quickly, slowly. In the and the corresponding non-terminals of these terminals are noun phrase, transitive verb phrase, intransitive verb phrase, article, adjective, noun, verb, adverb, and productions. Here and below are the production rules for CFG question. Sentence can be explained as noun phrase, transitive verb phrase, noun phrase, and sentences can be said as noun phrase and transitive verb phrase. Noun phrase is as article, adjective, noun, and noun phrase as the article, noun. These are also the rules in the previous slides we have seen. Now we move forward to the question we have to solve with the help of this production rules. In the first question, Use the set of production to show that each of these sentence is a valid sentence. We have to check each four sentences to check that this sentence is a valid or not. The first sentence says the happy hare runs. So we apply our production rules in according to this sentence. We can use the given set of production to show that the happy hare runs is a valid sentences. We start with the sentence symbol sentence, noun phrase, subject. The sentence can be written as noun phrase plus transitive verb phrase or noun phrase plus intransitive verb phrase. We choose noun phrase plus intransitive verb phrase because runs is an intransitive verb. Second, what is the article? Articles are the noun phrase, can be further expanded as article plus adjective plus noun or article plus noun. We choose article plus adjective plus noun because there is an adjective happy before the noun here. Specifics. Finally, we replace the non-terminals with the corresponding terminals. Article replaces with the and adjective replaces with the happy and noun replaces the hare. Intransitive verb phrase replaces hare. Already a terminal. Runs is already a terminal. Therefore, the complete derivation of this sentence, the happy hare runs, using the given production, is sentence noun phrase plus transitive verb phrase and article plus adjective plus noun plus intransitive verb phrase. So the sentence is made the happy plus hare plus runs. Hence the happy hare runs is a valid sentence according to the provided grammar. So this is how we can solve the CFG questions with the help of production rules. Second sentence we have given, the sleepy tortoise runs quickly. We know we can write sentence with the noun phrase, transitive verb phrase. This is we choose from the second rule. Noun phrase can be said as the adjective noun. This is we choose from the first rule for noun phrase. In this case, article is replaced the. Choose the only rule for article, and adjective is replaced by the sleepy. Choose the desired adjective. Noun is replaced by tortoise. Choose the desired noun. Third is in the intransitive verb phrase. Intransitive verb adverb. Choose the first rule for intransitive verb phrase. Intransitive verb is replaced run. Choose the desired verb. Adverb quickly, choose the desired verb adverb. Hence the sleepy tortoise runs quickly, providing its validity according to the grammar. Hence the sleepy tortoise runs quickly sentence is a correct CFG according to the production rules and the provided grammar. Like this first and second question, we can also solve C and D sentences. So we move forward to the second question. To derive a derivation tree for the question in uh, the happy hare runs and context-free grammar questions. The first question. In first we understand what is the graphical representation. Graphical representation of a derivation is called as a parse tree or derivation tree. The internal nodes are coupled with the non-terminals and represented left hand side of production rules. And the children's are external node represent the right hand side of corresponding production rules. In this slide we can see that we have the sentence in which we have two nodes, noun phrase and transitive verb phrase. In the noun phrase we have article, adjective, noun, and the article we have in this sentence is the, and the adjective in this sentence is happy, and the noun is in this sentence is have. So we described as according to the sentences. In the second node we have intransitive verb. Here intransitive verb is run, so we described in the right hand side node. Second, The tortoise pass here. The derivation tree of tortoise pass here. In this derivation tree, we have three nodes: noun phrase, intransitive verb phrase, and noun phrase. In the noun phrase, we have article and noun. In this sentence, the article is the, and in the noun we have tortoise, and in the transitive verb we have the transitive verb. In this sentence we have passes, and noun phrase, in the noun phrase we have articles and noun. In the in this sentence article and nouns are the and have. In this question we have given a question. The question says construct a phrase structure grammar that generates all signed decimal numbers consisting of a sign either plus or minus, semicolon, a negative, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by a positive integer, where initial zeros in an integer are follows. We have given terminals and non-terminals. Here terminals are plus, minus, 0, 1, 2, 3, 4 up to 9 and many more. Here our non-terminals are sentences, sign, digit, string, decimal, fractions are here. So here is a phrase structure grammar that generates all signed decimal numbers consisting of a sign either plus or minus, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by a positive integer. Initial zeros in an integer are as follow. These are the production rules. First we say that s. So s is a sign integer for decimal fraction. The start symbol s represents the entire signed decimal number. And the first rule, s is assigned to sign, integer, decimal fraction or positive number, are breakdowns the signed decimal numbers into three components: a sign, a integer, and a decimal fraction, a positive number. The second rule is sign plus defines the two possible signs plus and minus. And the third rule, integer digit, 0, integer, and empty. In this, a 0, integer, and empty defines the integer part of the number. It can be empty, a single digit, or a 0 followed by an integer. This allows for leading zeros in the integer. The fourth rule, digit 0, 1, 2, 3, 4, 5 up to 9 defines the valid digits 0 to 9 that can be used in the integer and decimal parts of the number. The fifth rule, decimal fraction digit sequence. In this we have positive number, 3 times of positive numbers. In the short we can write this a decimal fraction assigned to dot digit sequence, and this can be empty. Defines the decimal fraction part of the number. It can be empty or no decimal parts, or consist of a decimal point followed by a sequence of digit sequence. The sixth and last rule we have, the digit sequence is digit. Defines a sequence of digit. It can be a single digit or a digit followed by another sequence of digit. This grammar can generate all possible signed decimal numbers, including numbers with leading zeros, numbers with no decimal parts, and numbers with trailing zeros after the decimal points. In this question we have the question given, give the Backus-naur form of this grammar. These are the grammar: sentence, sign, integer, positive integer, digit, non. We explain this. So the first line, sentence, tell us this is a non-terminal symbol, represents the entire signed decimal number. And the sign symbol, this is a non-terminal symbol, represent the optional sign either plus or minus. And the pipe symbol indicates a choice between these 2 points, these 2 options. And third one is integer. This is a non-terminal symbol, represents the integer part of the number. It can be a single digit, digit or a sequence of digit, integer, digit. This allows for leading zeros in the integer. And fourth is digit. This is the non-terminal symbols, a single digit ranging from 0 to 9. And second last is decimal fraction. This is also a non-terminal symbol, represents the optional decimal part of the number. It can be the empty string indicating no decimal or a period followed by a sequence of digit, positive integer. And last is epsilon. This symbol represents the empty string. A BNF accurately captures the structure of a given grammar, defining how valid signed decimal numbers can be formed. So this is how we can form Backus-naur form of this grammar. These are the derivation tree for this Backus-naur form grammar. We have two nodes in each diagram and have child nodes. Like signed integer, we have integer, and in the integer we have digit integer, and integer we have in the integer we have digit and integer. In integer we have digit, which is 9. And also in the second diagram, signed sign decimal integer, we have sign positive integer. In the positive integer we have non-zero, and in the integer we have integer, digit, and digit 3 1. In this question, we have given production rules in Backus-naur form for an identifier. If it can consist of one or more lowercase letters, at least 3 but no more than 6 lowercase letter, 1 to 6 uppercase or lowercase letter beginning with an uppercase letter, a lowercase letter followed by a digit or an underscore followed by 3 or 4 alphanumeric character, lower or uppercase letters and digit. These are the four questions we have given. We have to give production rules in Backus-naur form for an identifier. So first we understand what are these elements are used. First is identifier. It is used for represent the entire identifier. Second is letter, represents a single lowercase letter, and uppercase letter represents a single uppercase letter. And digit represents a single digit from 0 to 9. And fourth is alphanumeric, represent either a letter or a digit, allowing for mixed case identifier. Plus represents one or more occurrence of the preceding symbol, and in brackets and comma m represents a range of occurrence from n to m inclusive, and pipe symbol represent a choice between alternatives. We have given identifier for first question. We have to write in lowercase letter only. So we write letters, and so we write letter identifier and we write lowercase letters. And in second question we write identifier at least 3 but not more than 6 letter. So we have write from 3 to 6 letters, like letter, and then we separate them by a pipe symbol, and after that we have type letter for 4 times, and we have separate them for pipe symbol and same as this. And in the C question we have same as the B question. This is how we can create the production rules for Backus-naur form. In this question, given production rules in Backus-naur form that generates all identifiers in the C programming language. In can identifiers starts with a letter or an underscore that is followed by one or more lowercase letter, uppercase letter, underscores and digits. We have identifier, letter load, symbols and letters. We know that identifier represents the entire identifier. In this identifier, letters, identifier and symbol is represent, and in the letterize represent letters, and symbols represent letters digit, and letter represents lowercase letters and uppercase letter. So upper in lowercase letter we define each alphabet in lowercase symbols A B C D as usual, and in uppercase letter we use the um, alphabetical uppercase letter alphabets, and the digits we represents ranging from 0 to 9 digits. This is how we can form production rules in Backus-naur form. In this question is given production, we have to create production rules in extended Backus-naur form that generate all decimal numerals consisting of an optional sign, a non-negative integer, and a decimal fraction, that is either the empty string or a decimal point, followed by an optional positive integer optionally, preceded by some numbers of zeros. In these questions we try to understand what are this all the identifiers is used for what types of things. The numeral identifier represents the entire decimal numeral, and the sign identifier is used to represent the optional sign, either plus or minus, or the empty string. And in this case we have decimal represents the optional decimal part of the number. It can be decimal point followed by one or more digit plus or the empty strings. And in as we know that sign represent the optional sign, and we have in this integer. So integer represents the integer part of the number, and it can be sequence of one or more digits like this. The revised extended Backus-naur form accurately captures the intended grammar for decimal numerals, allowing for optional signs, non-negative integers including single zero, or optional decimal points or decimal fractions without leading zeros. This is how we can create production rules in extended Backus-naur form. In this question given, we have to produce production rules in extended Backus-naur for identifiers in the C programming language. We have given the answer is says that identifier represents letter symbols, and letters represents letter with pipe symbol, and symbol represents letters pipe symbol with digit. We have separate letters and digit with pipe symbol. And fourth is letter represents lowercase letter separated by pipes, and uppercase letter. In lowercase letter we have write lowercase alphabets, and in uppercase letter we have write uppercase alphabet. And in the digit we have represent the digits from 0 to 9. This is how we can produce extended Backus-naur form rules. In this question we have to solve for each of these string, determine whether it is generated by the grammar given for post-string notation. If it is, find the steps used to generate the string. First we have ABC, asterisk and plus. This expression says that we have two terms and we have add operator, and in the third lines we have three factors, and we have mul operator, and we have added by add operator. And in the third line we have identifier, three identifier, one mul operator, and last we have add operator. This is how a grammar ABC asterisk plus is generated for the postfix notation. And the B question x y plus plus is not generated by the grammar for the postfix notation. C expression we have given C what we have x y minus z and asterisk is generated like expression term, and we have two factors and mul operator, and in the third line we have expression factor mul operator, and fourth line term we have two terms add operator and plus factor and right mul operator, and in the second last we have two factors and one add operator and one factor and one mul operator, and in the last line we have identifier, two identifier, one add operator and one identifier, and last mul operator. This is how xy minus z asterisk can be generated for the by the grammar for postfix notation. Thank you for watching this video.